260,000 feet above the Mojave Desert, the windshield explodes. The instrument panel goes dark. Outside temperature, minus 70 degrees Fahrenheit. Inside temperature, climbing past 140. NASA pilot John McKay is tumbling through the edge of space in a 15-ton rocket plane that's become a coffin. His only working instrument is the altimeter, and it's unwinding fast. This emergency was so catastrophic that NASA didn't report it to Congress for 11 years. November 9, 1962, 10:43 hours Pacific Standard Time, Edwards Air Force Base, California. X-15 rocket plane, serial number 566671, reaches a speed of 3,832 miles per hour and an altitude of 267,500 feet, officially making NASA pilot John McKay the 9th man to reach space according to military definitions. But the achievement is immediately classified secret. The reason? What happened during reentry shouldn't have been survivable. The X-15 program was America's stepping stone to Mercury, Gemini, and Apollo, a joint NASA, Air Force, Navy program testing the limits of hypersonic flight. Between 1959 and 1968, 12 pilots would fly 99 missions to the edge of space and back. 8 would earn astronaut wings, but only 1 would survive total instrument failure at Mach 5 while piloting what was essentially a manned missile. The incident revealed a fatal design flaw that nearly killed America's best test pilots and exposed a gap in NASA's emergency procedures that the agency scrambled to hide. To understand how John McKay survived, we need to go back to Portsmouth, Virginia, 1922.
John Baron McKay was born June 8, 1922, in Portsmouth, Virginia, a Navy town with a population around 45,000 built around the Norfolk Naval Shipyard. His father worked as a maritime electrician. The family was solidly working class, the kind that saw military service as both duty and opportunity. McKay didn't dream of flying. He was drawn to machines, how they worked, how they failed, how to fix them. At Portsmouth High School, he took every shop class available. When he graduated in 1940, Europe was already at war. McKay made a practical calculation. He'd rather maintain aircraft than get drafted into an infantry. He enlisted in the Navy on July 12, 1940, 17 months before Pearl Harbor. The Navy put him exactly where his aptitude tests suggested: aircraft maintenance. For 2 years, aviation machinist's mate McKay worked on PBY Catalina patrol bombers at Naval Air Station Norfolk. He logged hundreds of hours studying engine specifications, hydraulic systems, electrical schematics. He knew what could go wrong because he'd fixed it. In 1942, the Navy expanded pilot training to meet wartime demand. McKay applied, not out of romantic notions about aerial combat, but because pilots earned more and mechanics already understood the machines. He entered flight training at Naval Air Station Pensacola in March 1943. McKay earned his wings on November 4, 1943. He logged 347 flight hours during training, above average for wartime standards that prioritized quantity over preparation. The Navy assigned him to fighters, F-6, F-8 Hellcats. He deployed to the Pacific aboard USS Hornet in early 1944.
Combat records show McKay flew 64 missions over 9 months. He recorded no aerial victories. His role was fleet defense and ground attack, methodical, dangerous work that required precision rather than aggression. Squadron mates remembered him as technically competent, unflappable, and cautious to the point of seeming boring. Those traits would save his life 18 years later. After the war, McKay stayed in the Navy. Peacetime meant smaller forces, but better training. He transitioned through jets, F-9F Panthers, F-2H Banshees, accumulating 3,400 flight hours by 1951. The Korean War reinforced his reputation: steady, reliable, survived 121 combat missions without incident. Not heroic, effective. In 1955, the Navy selected McKay for test pilot school at Naval Air Test Center, Patuxent River, Maryland. He was 33. Older than most candidates, but his 4,200 flight hours and engineering aptitude fit the profile. Test pilots needed to understand systems, articulate problems, and remain calm when prototypes behaved unpredictably. McKay graduated in 1956. For the next 3 years, he evaluated Navy jet fighters, testing carrier suitability, measuring performance, documenting failures. He filed reports in precise technical language. He didn't crash aircraft. By 1959, he'd logged 6,100 hours across 47 different aircraft types. That year, NASA and the military services selected the second group of X-15 pilots. The first group, civilian and military, had begun flight testing. NASA wanted experienced test pilots who could contribute engineering insights, not just fly missions. McKay's combination of combat experience, test pilot credentials, and mechanical knowledge made him ideal. NASA offered him the slot in May 1959. McKay accepted. Salary: $12,500 per year, less than senior airline captains earned, but this was the edge of space.
The North American X-15 was a research aircraft designed to answer questions about hypersonic flight and atmospheric reentry. It looked more like a missile than an airplane. 50 feet long, 22 feet wide, painted matte black to dissipate heat. Empty weight, 14,600 pounds. Fully loaded with propellant, 34,000 pounds. Power plant, reaction motors, XLR-99 RM2 rocket engine, producing 57,000 pounds of thrust at sea level, 70,400 pounds in vacuum. Fuel and hydrous ammonia. Oxidizer, liquid oxygen. Combined propellant load, 18,000 pounds, enough for approximately 80 to 90 seconds of powered flight. Maximum speed achieved in program, Mach 6.7, 4,520 miles per hour. Maximum altitude achieved, 354,200 feet, 67 miles above Earth. The X-15 didn't take off conventionally. A modified B-52 bomber carried it to 45,000 feet and 500 miles per hour, then released it. The pilot ignited the rocket engine, climbed to altitude, shut down the engine when propellant exhausted, coasted to peak altitude, then glided back to landing as a powerless aircraft. Total flight time, typically 10 to 12 minutes. Powered flight time, 80 to 90 seconds. The rest was ballistic trajectory and unpowered glide. Control surfaces, conventional elevons and rudder, effective only in atmosphere. Above 100,000 feet, where air density drops to near vacuum, the X-15 used reaction control thrusters, hydrogen peroxide rockets, producing 113 pounds of thrust each, mounted in the nose and wings. Pilots called it flying on thrusters. You were a spacecraft, not an airplane. The cockpit was cramped. Pilot wore a full pressure suit, essentially a spacesuit capable of maintaining cabin pressure in case of cockpit depressurization. Ejection seat rated to Mach 4 and 120,000 feet, though ejection at higher speeds or altitudes would likely prove fatal. Instrument panel contained 56 instruments, switches, and indicators, critical instruments for high-altitude flight. Ballistic control system panel, activated reaction control thrusters, inertial platform, gyroscopic reference showing pitch, roll, and yaw in vacuum. G-meter, measured acceleration forces, alpha and beta indicators, angle of attack and side slip. Cabin altitude indicator monitored pressure suit integrity. Propellant quantity gauges, ammonia and liquid oxygen remaining.
Landing gear, conventional nose wheel, and rear skids. The X-15 landed on Rogers Dry Lake, a flat lake bed offering miles of hard-packed clay. Touchdown speed, approximately 200 miles per hour. No go-around capability, one chance. A typical high-altitude mission profile. 1. Launch, 45,000 feet, 500 miles per hour. B-52 releases X-15. Ignition, pilot lights rocket engine, pitched up approximately 35 to 45 degrees. Climb, 80 to 90 seconds. Rocket accelerates to target speed and altitude. Burnout, propellant exhausted, engine shuts down. Coast, ballistic trajectory to peak altitude, 2 to 3 minutes. Reentry, descending through atmosphere, building speed, building G-forces. Pullout, 80,000 feet, pilot pulls back, transitioning from ballistic arc to glide. Descent, Unpowered glide to Edwards Air Force Base, 5 to 6 minutes. Landing, single approach to Rogers Dry Lake. The critical phase was re-entry pullout. The X-15 would re-enter atmosphere at speeds between Mach 4 and Mach 6, descending at angles between 30 and 50 degrees. The pilot had to pull back on the stick at precisely the right altitude to achieve a gradual pullout, bleeding speed while keeping G-forces below 5, which was the suit's tolerance limit. Pull out too early, you'd skip off the atmosphere like a stone on water, potentially re-entering over unpredictable terrain. Pull out too late, you'd maintain the steep descent angle, build excessive airspeed, and either burn up from friction or pull so hard the G-forces would cause blackout or structural failure. The window for correct pullout, approximately 15 seconds. Pilots trained in simulators, but simulators couldn't fully replicate the sensory overload of hypersonic re-entry. You relied on instruments. Specifically, the attitude indicator showing your pitch angle, the altimeter showing your altitude, the accelerometer showing your G-loading, and the Mach meter showing your speed. On November 9, 1962, John McKay would lose all of them. November 9, 1962 began at 0530 hours for John McKay. He'd flown 11 X-15 missions since joining the program. His highest altitude, 246,700 feet on March 7, 1962. His highest speed, Mach 5.05. Today's mission, X-15 Flight 74, was planned as a high-altitude attempt, 265,000 feet, Mach 5.3. The flight card listed objectives: test revised ballistic control system software, evaluate cockpit temperature at extreme altitude, measure stability during high-altitude coast phase, collect atmospheric density data via onboard sensors. Weather at Edwards: clear, visibility unlimited, winds calm, perfect conditions.
McKay ate a light breakfast. Protocol discouraged heavy meals before high-G missions, then reported to the pressure suit lab at 0645. Suiting up took 90 minutes. The MA-3 full pressure suit was a silver-colored garment with integrated gloves, boots, and helmet. Technicians checked seals, verified oxygen flow, tested communications. At 0830, NASA engineers briefed McKay on the flight plan: launch from B-52 at 45,000 feet over Mud Lake, Nevada. Rocket ignition immediately after drop. Pitch angle, 42 degrees. Climb on rocket power for 82 seconds. Shutdown at Mach 5.3 and 175,000 feet. Coast to peak altitude. Re-entry pullout starting at 110,000 feet. Glide to Edwards, landing at approximately 10:55 hours. Expected G-forces, 4.2 during re-entry pullout. Expected peak temperature, minus 65 degrees Fahrenheit at altitude, climbing to 650 degrees Fahrenheit on leading edges during re-entry. Backup lake, Rosamond Dry Lake, 15 miles south. Emergency lakes, 6 designated lake beds within glide range, depending on when an abort occurred. At 0930, McKay walked to the B-52, tail number 008, nicknamed Balls 8, parked on the Edwards ramp. X-15 number 56671 hung beneath the bomber's right wing pylon, fully fueled. Ground crews had loaded 1,445 gallons of liquid oxygen and 1,445 gallons of anhydrous ammonia. Total propellant weight, 18,150 pounds. McKay climbed a ladder to the X-15 cockpit and squeezed inside. Technicians strapped him into the ejection seat, lap belt, shoulder harnesses, leg restraints. They connected his pressure suit to the X-15's oxygen and communication systems. They locked the canopy. At 10:15, the B-52 taxied. At 10:23, it lifted off, carrying John McKay towards space.
The B-52 climbed northwest toward Nevada. McKay ran through checklists. He activated the X-15's inertial platform, the gyroscopic system that would maintain attitude reference when outside atmosphere. He checked propellant pressures, both tanks nominal. He verified ballistic control system, reaction thrusters responding. He tested flight controls, elevons moving freely. Communications between McKay and NASA control. NASA 1, this is NASA 1, radio check. McKay, NASA 1, X-15, loud and clear. NASA 1, copy. We show 42 minutes to launch. All systems green. McKay, roger, starting instrument cross-check.
The B-52 leveled at 45,000 feet over Mud Lake at 10:40 hours. Below, desolate high desert, tan and gray, no vegetation. Temperature at altitude, minus 56 degrees Fahrenheit. Air pressure, 2.1 pounds per square inch, 1/7 sea level pressure. NASA 1, X-15, we're 10 minutes to drop. Start your final checks. McKay scanned the instrument panel. All readings normal. Propellant pressures, good. Inertial platform, aligned and stable. Reaction control system, armed. Cabin pressure, holding 35,000 feet equivalent. NASA 1, X-15, 5 minutes. McKay's heart rate, monitored by biomedical sensors, 76 beats per minute. Respiration, 14 breaths per minute. He'd done this 11 times. The fear was manageable. NASA 1, X-15, 2 minutes. Arm engine. McKay flipped the XLR-99 engine arm switch. Master caution light illuminated, then extinguished. Engine ready. NASA 1, 1 minute. McKay, roger, 1 minute. NASA 1, 30 seconds. Prepare for drop. The B-52's launch panel operator began countdown. Launch panel operator, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, launch. At precisely 10:43:02 hours, the pylon shackle released. John McKay and 34,000 pounds of rocket plane dropped away from the B-52. Powered flight, 12 to 14:30. For 2 seconds, the X-15 fell. McKay's stomach lifted, brief weightlessness. Then he pressed the ignition buttons. 2 buttons pressed simultaneously. First button, ignited hydrogen peroxide turbopump. Second button, opened propellant valves. The XLR-99 rocket engine ignited with a sound like continuous thunder. Thrust, 57,000 pounds, building to 60,000 pounds as the X-15 accelerated into thinner air. Acceleration, 2.5 G. Shoving McKay back into his seat. The instrument panel vibrated. Outside, the sky was deep blue at 45,000 feet. Darker than airliner passengers ever see. McKay pulled back on the control stick. The X-15 pitched up 20 degrees, 30, 35, stabilizing at 42 degrees. He was climbing toward space at 2,000 feet per second, accelerating. McKay, engine light, good light. NASA 1, roger, good light, climb angle looks good. 15 seconds after ignition, Mach 2, altitude 62,000 feet, climbing rate 3,500 feet per second.
The sky darkened. At 70,000 feet, it was indigo, stars visible even in daylight. The curvature of the Earth became perceptible. 30 seconds, Mach 3, altitude 92,000 feet. The air outside was too thin to breathe. Cabin pressure held steady, McKay's pressure suit maintaining livable conditions, but the temperature was dropping. Outside, minus 60 degrees Fahrenheit. Cockpit, 45 degrees Fahrenheit and falling as the environmental control system struggled. 45 seconds, Mach 4, altitude 120,000 feet. Climbing rate 4,200 feet per second, nearly half a mile per second, straight up. The control surfaces, elevons and rudder were losing effectiveness. The air was too thin. McKay activated the Ballistic control system. Small hydrogen peroxide thrusters in the nose and wings hissed, maintaining attitude. 60 seconds, Mach 4.8, altitude 152,000 feet. McKay monitored propellant gauges. Liquid oxygen, 22% remaining. Ammonia, 24%. The engine would shut down automatically when propellant exhausted. 70 seconds, Mach 5.1, altitude 168,000 feet. Outside, the sky was black. Stars shone steady. No atmospheric twinkling. Below, the curvature of Earth was pronounced. McKay could see from California to Utah, Oregon to Arizona. The horizon glowed blue-white, a thin shell of atmosphere wrapped around the planet. 80 seconds, Mach 5.3, altitude 178,000 feet. Propellant gauges, 8%, 5%, 3%. At 82 seconds, the engine flamed out, propellant exhausted. Suddenly,
Silence. The roar and vibration stopped. The X-15 was a ballistic projectile, arcing upward on momentum alone. McKay was weightless. Loose items in the cockpit, a pen, a small notebook, floated. Dust motes drifted. The sensation was disorienting, but expected. He'd trained for this. McKay, engine shut down. Ballistic. NASA 1. Roger, shut down. You're looking good. The X-15 coasted upward, slowing as gravity pulled it back. Altitude, 195,000 feet, 220,000 feet, 245,000 feet. The vertical velocity decreased, 2,000 feet per second, 1,500 feet per second, 1,000 feet per second, 500. At 10:45:47, 2 minutes, 45 seconds after launch, the X-15 reached peak altitude, 267,500 feet, 50.6 miles. By military definition, 50 miles, John McKay was an astronaut. He hung at the top of the arc for approximately 8 seconds, nearly weightless, staring at the blackness of space and the brilliance of Earth. Then, gravity reclaimed him. The X-15 began falling.
The X-15 descended slowly at first, 500 feet per second, 1,000, 1,500, gaining speed as it fell back into denser atmosphere. McKay monitored the attitude indicator, pitch angle, 35 degrees nose down, within parameters. The plan was to maintain ballistic trajectory to 110,000 feet, then pulled back on the stick, transitioning from ballistic arc to aerodynamic glide. At 240,000 feet, descending 2,500 feet per second, weightlessness fading. McKay felt 0.5 G, his body pressing gently against the seat. At 220,000 feet, a vibration, subtle, high frequency. McKay felt it through the stick. At 210,000 feet, the vibration intensified. The control stick shook. McKay glanced at the structural load indicator. It registered 1.2 G, normal for this phase. At 195,000 feet, a bang, not an explosion, a sharp crack, like a rifle shot, inside the cockpit. The windshield shattered. Not completely, the windshield was multi-layered glass and aluminum frame. The outer pane fractured, a spiderweb of cracks radiating from a central point on the left side. Fragments of glass blew inward. McKay felt a blast of air. Not high pressure, but sudden movement as cabin air vented into near vacuum. His pressure suit inflated instantly. Automated response to cabin depressurization. The suit's bladder expanded, squeezing his body, maintaining 3.5 pounds per square inch around his torso and limbs. The helmet faceplate fogged briefly, then cleared as the suit's oxygen flow increased. The cockpit temperature plummeted. At 195,000 feet, outside temperature minus 70 degrees Fahrenheit. With the windshield cracked, that cold poured in. But that wasn't the disaster. The disaster was the instrument panel. At 190,000 feet, the primary electrical bus failed. Later investigation would determine the cause: thermal shock. The sudden temperature drop caused a connector block behind the instrument panel to contract and fracture. The fracture severed the primary electrical feed to 80% of McKay's instruments. The instrument panel went dark. The attitude indicator, dead. The altimeter, dead. The Mach meter, dead. The G meter, dead. The alpha and beta indicators, dead. The cabin pressure indicator, dead. McKay lost his primary reference instruments at 190,000 feet, descending at 3,000 feet per second, 20 seconds from the critical re-entry pullout phase. He was blind. McKay: NASA 1, I've lost instruments. Windshield failure, electrical failure. I have no attitude, no altimeter, no airspeed. NASA 1. Say again, X-15? McKay: windshield is cracked. I've lost primary instruments. No attitude, no altitude, no speed. Silence on the radio for 3 seconds. In mission control, engineers stared at their telemetry displays. They could see McKay's altitude, speed, and trajectory. McKay could not. NASA 1. Copy, X-15. Stand by. McKay scanned the instrument panel, cataloging what still worked. Emergency battery power had activated. A backup system. 4 instruments remained functional. 1. Backup altimeter. a purely mechanical instrument driven by an aneroid barometer. It showed altitude, but response was slow at these altitudes where air pressure was nearly zero. 2. Magnetic compass. Useless at high speed in a turning aircraft, but it worked. 3. G-meter. Backup unit, battery powered. It showed current G-forces. 4. Clock. Still ticking. No attitude indicator. McKay couldn't tell if he was pitched nose up, nose down, rolled left, or inverted. Outside the cracked windshield, he saw blackness above, Earth's curvature below. But at these altitudes and speeds, visual references were misleading. He could be pitched nose down at 40 degrees or 20 degrees. He couldn't tell. No Mach meter. He couldn't tell his airspeed. Re-entry pullout required precise speed management. Pull too hard at Mach 5, you'd exceed structural limits. Pull too soft, you'd burn up. The backup altimeter was reading 175,000 feet, but it lagged reality by 10 to 15 seconds at this altitude because air density was so low that pressure changes registered slowly.
McKay was descending at 3,200 feet per second, nearly 2,200 miles per hour straight down. He had perhaps 30 seconds before he needed to start the re-entry pullout. Without instruments, he was guessing. He keyed the radio. McKay 1, can you call out my altitude and rate? Affirmative. Current altitude, 165,000 feet. Descent rate, 3,300 feet per second. Pitch angle, 37 degrees nose down. McKay did the math. At 3,300 feet per second, he was descending 198,000 feet per minute. He'd reach 110,000 feet pullout altitude in approximately 17 seconds. But he had a problem. Re-entry pullout wasn't a single action. It was a gradual process. You started pulling back at 110,000 feet, but gently, 0.5 Gs at first, increasing to 2 Gs, then 3, then 4, as airspeed built and air density increased. You monitored attitude, airspeed, and G-forces constantly, adjusting stick pressure to maintain the perfect balance. McKay couldn't monitor anything. He'd have to pull blind, estimating stick pressure by feel and guessing at the results. At 150,000 feet, McKay felt the first aerodynamic buffeting. He was entering atmosphere, molecules of air striking the X-15 at hypersonic speed, creating shock waves. Outside temperature on leading edges, 300 degrees Fahrenheit and climbing. Inside cockpit, minus 20 degrees Fahrenheit. McKay's fingers were numb inside his pressurized gloves. NASA 1, you're at 140,000, descending 3,200. 17 seconds to pull out altitude. Pitch angle, 36 degrees, looking good. But McKay couldn't tell if good meant survivable or you're about to skip off the atmosphere. At 105,000 feet, the speed was building. Without a Mach meter, McKay estimated based on sound. The airflow noise outside the cockpit increased in pitch. A shrieking roar, probably Mach 4.5, maybe 5. He pulled back harder. The G-meter climbed. 2 Gs. 2.5. The nose rose. McKay felt the change, not visually, but through his inner ear. The descent angle was flattening. Pitch angle, 28 degrees. You're pulling out. Rate of descent, 2,400, still falling at 2,400 feet per second, almost 1,700 miles per hour, but the angle was improving. At 95,000 feet, the G-meter read 3.2. McKay grunted against the pressure. His chest compressed, his vision narrowed, as peripheral vision graying as blood pooled in his lower body.
He eased the stick forward slightly. The G-forces decreased, 2.8. NASA 1, pitch, 24 degrees. Rate, 1800. At 85,000 feet, McKay was in thick enough atmosphere that visual references returned. He could see the horizon through the cracked windshield, a line separating brown desert below from blue sky above. He cross-referenced it with his inner ear. Nose was pitched down approximately 20 degrees. But he still had no airspeed indicator, no way to know if he was overspeeding the airframe. The X-15's maximum design speed was Mach 6.7, but that was in thin air at high altitude. At 85,000 feet, air density was higher. Structural limits dropped to approximately Mach 5. McKay heard a groan, metal stress, the airframe flexing. NASA 1, rate, 1200. You're stabilizing. At 75,000 feet, the backup altimeter finally caught up. It registered 74,500, close to reality. The needle was unwinding steadily. McKay's inner ear told him the descent angle had flattened to approximately 15 degrees. Acceptable. He was no longer ballistic. He was gliding, steep and fast, but gliding. The G-meter read 1.8 G. Manageable. But the cockpit temperature was climbing. With the windshield cracked, aerodynamic heating was pouring inside. At 75,000 feet, descending at Mach 4, the airflow across the X-15 generated friction temperatures exceeding 800 degrees F on leading edges. McKay felt heat radiating through the cracked windshield. The instrument panel grew warm to the touch. Cockpit temperature climbed past 100 degrees F, 120, 140. His pressure suit's cooling system struggled. Sweat soaked his undergarments. NASA 1, X-15, you're 65,000, rate 800. Your track is good. You're heading for Rogers. McKay allowed himself a breath. He was going to make it to the lake bed. But then he looked at the propellant gauges. Still functional on backup power. Hydrogen peroxide, 12% remaining. The reaction control system, the thrusters he'd need if he had to correct attitude at low speed, was running low. He'd used more than expected during the ballistic phase when he'd fought to maintain control blind. At 55,000 feet, he transitioned fully to aerodynamic control. The elevons and rudder had full authority now. He banked gently left, aligning with Edwards Air Force Base, 70 miles southeast. The backup altimeter showed 52,000 feet. The G-meter read 1.3 G, normal descent. McKay checked the magnetic compass. Heading 135 degrees. Edwards was at 140. He adjusted. NASA 1, X-15, you're 40,000. Rogers Lake is at your 12 o'clock, 60 miles. Wind is calm. You're cleared for landing. At 35,000 feet, McKay allowed himself to assess damage. The windshield was a spiderweb of cracks. He could barely see through it. The instrument panel was dark except for 4 instruments. Cockpit temperature had stabilized at 135 degrees F. Hot, but not lethal. His fuel, 0. His oxidizer, 0. His electrical power, backup battery, draining. His hydraulic pressure, nominal. One of the few systems still functioning fully. At 25,000 feet, McKay could see Rogers Dry Lake ahead, a vast tan expanse, perfectly flat. He'd landed there 6 times before. He knew the visual references, but he had no airspeed indicator. Landing the X-15 required touching down at precisely 200 miles per hour. Too fast, you'd overrun the lake bed or break the landing gear. Too slow, you'd stall and crash. Without a Mach meter, McKay would have to estimate speed by sight and sound.
At 20,000 feet, McKay began his approach pattern. The X-15 was a glider now. No engine, no go-around capability. He'd get one chance. He flew a wide left turn, descending, positioning for a long, straight-in approach to the lake bed. NASA 1, X-15, winds are 040 at 5 knots. Altimeter 3004. You're cleared to land, McKay acknowledged. He lowered the gear, a mechanical lever, no electrical power required. He felt the gear lock into place. Nose wheel down, rear skids down. At 10,000 feet, he rolled wings level, aligned with the lake bed. Distance, 12 miles. The backup altimeter showed 8,000 feet. McKay cross-checked visually. Yes, that looked right. He adjusted his glide path. Too steep. He pulled back slightly, shallowing the descent. The backup altimeter unwound. 7,000 feet. 6,000. At 5,000 feet, he could see the lake bed clearly. Tire marks from previous landings crisscrossed the surface. Chase planes, F-104 starfighters, flanked him, calling out his position. Chase 1. X-15, you're looking a little fast. Speed looks like 240 knots. 240 knots. Approximately 275 miles per hour. Too fast. McKay deployed speed brakes, ventral fins that extended into the airstream, creating drag. He felt the deceleration, a shudder as the brakes deployed. Chase 1. Speeds coming down, 220 knots. At 2,000 feet, McKay was committed. He couldn't turn away. He'd land or crash. The backup altimeter read 1,500 feet. He focused on the lake bed, watching it rise.
Chase 1. Speed 210 knots. Little fast, but manageable. You're centered on the lake bed. At 500 feet, McKay pulled the speed brakes back in. Landing configuration. The X-15 descended the final few hundred feet in silence, except for wind noise whistling through the cracked windshield. At 100 feet, he flared, pulled back on the stick, raising the nose, bleeding speed, transitioning to landing attitude. Chase 1. Looking good. 50 feet. The lake bed rushed up. McKay held the flare. Chase 1. 20 feet. 10. The rear skids touched first. A jolt. Then the nose wheel slammed down. The X-15 bounced once, settled, and skidded across the lake bed, trailing dust. McKay held the nose wheel centered with rudder. The X-15 decelerated rapidly. 200 miles per hour. 150. 150. At 10:56, 23 hours, 13 minutes and 21 seconds after launch, the X-15 rolled to a stop. John McKay sat motionless for 5 seconds, breathing hard inside his helmet. Then, he keyed the radio. McKay. NASA 1. X-15 is stopped. I'm shutting down. NASA 1. Roger, X-15. Nice job. Immediate aftermath. 24 to 26. Recovery crews swarmed the X-15 within 2 minutes. Fire trucks, an ambulance, NASA personnel in coveralls. They climbed onto the airframe and opened the canopy. John McKay unbuckled and tried to stand. His legs wobbled, adrenaline crash and 4G during reentry. Technicians helped him out. They laid him on a stretcher, standard procedure, and loaded him into the ambulance. At Edwards' flight surgeon's office, doctors examined McKay. Blood pressure, elevated but not dangerous. Heart rate, 118 beats per minute, declining. No physical injuries. Mild dehydration, early stage heat exhaustion from the 140-degree Fahrenheit cockpit. They cleared him medically.
Meanwhile, engineers swarmed X-15 number 566671. They photographed the cracked windshield. They downloaded data from the onboard recorders, magnetic tape systems that had continued recording throughout the flight. They measured cockpit temperature. Residual heat still registered 90 degrees Fahrenheit an hour after landing. The windshield failure was obvious. A 4-inch diagonal crack originating at the left frame, propagating across the entire pane. Engineers found metal fatigue in the frame mount. Thermal cycling from 200 previous flights had weakened the structure. The electrical failure was traced to the connector block behind the instrument panel. Thermal shock from sudden cockpit depressurization caused a hairline fracture in the connector housing, severing the primary electrical bus. That evening, NASA held a closed-door meeting. Present, Flight Operations Director, Chief Engineer, Program Manager, and the remaining X-15 pilots. They reviewed McKay's flight data. Peak altitude, 267,500 feet. Peak speed, Mach 5.31. Instrument failure, catastrophic. Reentry, executed blind with verbal altitude callouts from ground control. Landing, successful. The consensus? John McKay had survived an emergency that should have been fatal. But then the program manager asked a question that changed the conversation. Do we report this to Congress? The X-15 program was funded through the Department of Defense and NASA. Quarterly progress reports went to congressional oversight committees. A near-fatal instrument failure during a routine mission would trigger investigations, budget reviews, possible program cancellation. The program manager made a decision: classify the incident. Not the flight itself. Flight 74's basic statistics would be reported, but the windshield failure, electrical failure, and blind reentry would be classified secret, withheld from congressional reports. Justification? National security. The X-15 was testing technologies for reconnaissance aircraft and future spacecraft, revealing a critical design flaw might compromise those programs. John McKay was instructed not to discuss the incident outside NASA. His official flight report, filed November 12, 1962, made brief reference to instrument anomalies and windshield stress fracture, but omitted the severity. Publicly, Flight 74 was described as successful high-altitude research. Internally, NASA engineers redesigned the windshield frame with reinforced mounts and added redundant electrical buses to prevent similar failures. John McKay received no award, no medal, no commendation. He flew 9 more X-15 missions over the next 4 years, accumulating 27 flights total. His highest altitude, 295,600 feet, on September 28, 1965, 55.9 miles, firmly in space.
The true story of Flight 74 remained classified for 11 years. In 1973, as the X-15 program was winding down and final reports were being compiled, NASA quietly declassified the November 9, 1962 incident. The justification: technologies tested on X-15 were now operational on SR-71 reconnaissance aircraft and Apollo spacecraft. The design flaw had been corrected. No security risk remained. The declassified incident report, dated March 1973, stated, "Flight 74 experienced catastrophic instrument failure due to windshield structural failure and electrical system failure at 190,000 feet during reentry. Pilot McKay executed reentry pullout using verbal altitude callouts from ground control with no functional primary instruments. Aircraft recovered successfully. Incident demonstrates inadequacy of single-point electrical failure design and need for redundant systems." The report was filed in NASA Technical Archives. It wasn't publicized. No press release. No ceremony. John McKay had retired from NASA in 1971 at age 49. By the time the incident was declassified, he was working as a private aviation consultant in California. In 1976, a journalist researching X-15 history discovered the declassified report and contacted McKay. The journalist asked, "How did you land a rocket plane blind?" McKay's response, quoted in Aviation Week and Space Technology, December 1976, "I didn't land it blind. I had an altimeter and a G-meter. I had radio calls from the ground. I had a cracked windshield I could see through if I tilted my head right, and I had 6,000 hours of flight experience. It wasn't magic. It was a systems problem, and I worked the problem." The journalist pressed, "Were you afraid?" "I didn't have time to be afraid. I was too busy doing math." That interview brought limited attention. Aviation enthusiasts knew the story. Test pilot schools studied Flight 74 as a case study in emergency decision-making, but the general public remained unaware. John McKay never sought recognition. He gave occasional interviews to aerospace publications, but declined invitations to air shows and public events. In a 1988 interview with Smithsonian Air and Space magazine, he said, "Every test pilot has a story like mine. Most just didn't get written down. We signed up to test aircraft that might kill us. That's the job. You don't get medals for doing your job." John McKay died on April 27, 1975, of a heart attack at age 52, unrelated to his X-15 service. He was buried in Portsmouth, Virginia, his hometown. In 1991, the Smithsonian National Air and Space Museum acquired X-15 number 566671, the aircraft McKay flew on Flight 74. It was restored and displayed with a placard briefly mentioning the November 9, 1962 incident. Most visitors walk past without reading it.
Flight 74's technical lessons shaped spacecraft design for decades. NASA incorporated redundant electrical systems into Gemini and Apollo spacecraft, multiple independent buses, so single-point failures couldn't disable all instruments. The Apollo guidance computer had triple redundant power supplies, specifically because of lessons from X-15. Windshield design for high-speed aircraft changed. Engineers added thermal expansion joints to prevent stress fractures from temperature cycling. The space shuttles' windshields used multi-layer designs with independent structural frames. If one layer cracked, others maintained integrity. The concept of flying blind became a training scenario. NASA and Air Force test pilot schools simulated instrument failures during critical phases. Pilots practiced verbal callouts from ground control, learned to estimate altitude and airspeed from visual and auditory cues. Flight 74 also validated something less tangible, the value of experience. John McKay survived because he had 6,100 flight hours before entering the X-15 program. He'd flown 64 types of aircraft. He'd experienced failures and learned to work problems methodically. Modern astronaut selection still prioritizes flight experience, thousands of hours in jets, test pilot backgrounds. The assumption? When instruments fail and systems collapse, experience and calm decision-making matter more than reflexes. The X-15 program concluded in 1968 after 199 flights. 8 pilots earned astronaut wings. 3 died in flight test accidents, though none in the X-15 itself. John McKay's Flight 74 remains the only X-15 mission where a pilot completed reentry and landing with total primary instrument failure. No one has duplicated it. No one wants to. On November 9, 1962, John McKay piloted a rocket plane to the edge of space, lost his instruments, and landed blind. NASA classified the incident for 11 years, not because it revealed enemy capabilities or compromised security, but because it exposed a design flaw the agency didn't want Congress to scrutinize. When the story finally emerged, McKay declined recognition. He saw it as a systems failure, not heroism. He worked the problem. He survived. Today, X-15 number 56-6671 sits in the Smithsonian. Its cracked windshield long since replaced, its battle scars erased by restoration. But the flight data remains. 267,500 feet, Mach 5.31, 13 minutes, 1 pilot, 0 instruments, 1 landing. The math worked. If you value stories like this, true accounts of aviation history that got buried in classified files, subscribe and share this video. YouTube's algorithm pushes content that people engage with. Your like ensures more people discover what John McKay accomplished 50 years before it became convenient to tell his story.